In this question, we're given a solid cylinder that is radiating power. It has a length that is 10 times its radius. I'll just make a quick sketch. And the length here is basically, if the cylinder has a radius r, then the length is nr. It is cut into a number of smaller cylinders, each of which has the same length. Each small cylinder has the same temperature as the original cylinder. So we have cut it basically, I would say, perpendicular to the axis of the cylinder. And the temperatures are the same for all of these objects now. The length L is the same here, but we don't know anything about it. And of course, the radius, by the way, is still smaller. The total radiant power emitted by the pieces is twice that emitted by the original cylinder. So I can represent this as the power of the pieces is 2 times the power of the big cylinder itself. I'll name this the original cylinder. How many smaller cylinders are there? So let's start by, obviously, we can rearrange this equation into some ratio. And then maybe we can substitute the expression for each power, which is basically given by the formula for radiation heat transfer. And afterwards, we can check what terms are gonna cancel out. So for the radiation heat transfer, we are given that the power is equal to the emissivity times sigma, which is the Stefan-Boltzmann constant, times the temperature, the absolute temperature of the object, power 4, times the surface area of the objects. Now here we have n pieces and each one has an area A. So I'm gonna basically just write down the power of one piece to be equal to E sigma T power 4 times the area, the surface area of this piece, multiplied by n because we have n pieces. For the original cylinder, I will have E sigma T power 4. I wrote T for both the pieces and the original cylinder because the temperatures are the same. And the area, I will write it as A of the original cylinder. And this is equal to 2. You can see how all of these terms cancel out. And what we are left with is the number of pieces, the area of one piece. Basically, that's just one piece, right? And all of these are the pieces. The area of the original cylinder is in the denominator, and this is equal to 2. Again, the question is to find how many small cylinders are there. So we're interested in finding n as a matter of fact. So let's just try to substitute the areas. This is the surface area. And the surface area of the cylinder is essentially going to be equal to the area of the curved face plus 2 times the area of each end. These are two circular faces. The curved face it has a surface area equal to 2 pi RL for any cylinder. And the circular faces each will have an area of pi r squared. Remember, L is equal to, so let's just substitute. For a single piece, the length is L. We don't know anything about it, but one thing I know is that if you sum all of these L's for each piece, they should add up to 10R, right? The original length of the original cylinder. So, and all of these L's, if I add them up, they're equal to N times L, the length of one piece times the number of pieces I have. And these should be equal to 10R. So the length of each piece, one piece, is equal to 10R over N. So if I want to write the area of one piece, this is going to be n into the area of the curved face, which is 2 pi r times L. L is the length of one piece, which we just wrote as 10 r over n plus 2 pi r squared. Now, the area of the original cylinder is 2 pi r L. Now, the length of the original cylinder is 10 r plus 2 pi r squared. This is also equal to 2. So you can see that we have n, this is what we're interested in, and we have r in our formulas. However, you will see that r is gonna cancel out. So I'll just expand my expression in the numerator. It will be 2 pi r times 10 r over n plus n 2 pi r squared divided by 2 pi r times 10 r plus 2 pi r squared. And this is equal to 2, right? So I'll continue with my substitution, and then n and n here cancel out. We end up with 20 pi r squared plus n times 2 pi r squared divided by 20 pi r squared again plus 2 pi r squared, and this is equal to 2. You can see how the only unknown I have is n. So I can just substitute. And one thing we also notice is if you take r squared as a common here and here, then it's gonna cancel out with the denominator, which has r squared as well. And we can also take like pi as a common, or 2 pi. So if you take 2 pi from here and here, you end up with 10 plus 1 in the denominator and 10 plus n in the numerator, and all of these just cancel out. So I just got that 10 plus n equals 22, so n is equal to 11. Actually 12, sorry about that. So we have 12 pieces.